Swayam Prabha. Digital India. Educated India.
Restroom, a few minutes. Anyone? No? Okay, shall we start? Okay, so thank you. First, thank you all for being here. And as I came to know a few weeks back that you are here on a prestigious program, RSIC Summer Internship Program. I had heard about the program earlier. One of our physics department, Professor V. Balakrishnan, is a very eminent physicist who started it along with others quite a few years ago. I never got a chance to participate here. This is the first time I'm participating. So I'm from the Department of Physics, and I think some of you are working in my lab. Who are there? Yeah, they are working. It's just across the building, the next building. My lab probably can be seen from here. It's just across. So again, this presentation, if you find it difficult to understand at any stage, you can interrupt me, obviously, and I'll sometime, time permits or any other time, since almost all of you are from Chennai, so I welcome you within RSIC program or otherwise. Anytime you would like to visit, see the things I am showing here in a more direct manner, you are welcome. Okay. Our contact numbers are given in the brochures. So, but this is a research level presentation, I'll tell you. But very consciously I have kept it at that. I didn't want to include too many animations and cartoons and all that, because you will get a feel or flavor of the research that is done, but not to be worried. I'll take you through the presentation in terms of a storytelling, so that you understand. So, an exciting world of one-dimensional nano and heterostructures. I'll not explain all the terms here to keep it more focused and simple. So, the first thing is nano. How small is nano? What do you understand by the word nano? 10 to the power minus 9, all of you know. Yes, great, 10 to the power minus 9. You go to Wikipedia, you go to Google, or nowadays ChatGPT, you get tons of information on what is nano. But the question is, why people are so interested in nano? Keep the phones in silent, please. Why we are interested in nano? Behavior is different, very good. Behavior of what? Of the material? Of the material, first thing. And if you look deeper, this is the behavior of atoms. More importantly, is the behavior of electrons. Electrons control the world. Electrons. Okay, we are not going to subatomic physics. If you say, if you are familiar with nuclear physics, you say, no sir, it is not the electrons. It is the quark, leptons, baryons, quark, gluon, plasma. Those are more important than electrons because they make an electron. We are not going to sub-electronic level. We are not going to split up here. So, electron, for all our practical purposes, electron is our person of interest. We want to arrest electron. No, person of interest. Investigators say no, or police say person of interest, whom they want to arrest or problem. So, nanostructure is that where size is small, 10 to the power minus 9 meter is the general definition. But more particularly, I will tell you before going into even the first slide. I can spend half an hour or more even on the first slide. But so, as I said, I will tell you a story. Don't worry about how many slides I have, what I am going to tell. Don't worry about that. Just enjoy and listen to the story. So, what happens at the nanoscale? I told you that the electrons are confined. Confined means you are putting the electron in a space where the electron do not have sufficient space. This corridor is wide enough and I am walking, okay, I am walking, I am very comfortable, I tell you hi, hello, shake hands. Imagine this corridor becomes narrow, so narrow that my shoulders touch the wall. will I be able to walk so comfortably? I will not be able to walk so comfortably. So what happens? If I am the electron and this corridor is a material through which the electrons are passing, then what is happening? As soon as you make the material towards smaller dimensions, nano, then these electrons are feeling the confinement. You understand? Confinement. So what is happening? Movement of electrons are changing. That is what you call as behavior. So one of the primary thing is that the electronic properties, for example, the simplest electronic property is conductivity. You know conductivity? Conductivity will be changing, and similarly many other things are changing. So what people have found, so the first thing you should realize that means what? Nano was there all the time, 10 to the power minus 9, small material was all the time there. Then why only recently, last few decades, people have started talking about the nano? The reason, there are two folds. One, that the discovery of a branch of physics called quantum mechanics. Quantum mechanics tells us that all these electrons and protons, neutrons, those are these particles which are extremely small. They do not obey the laws of classical physics or Newtonian physics. Why? Because their Heisenberg uncertainty principle, you have heard, no? You all of you know. I am not going to talk about those things. Heisenberg uncertainty principle kicks in, and when Heisenberg uncertainty principle kicks in for all these small particles, then their behavior are governed by the branch of physics called quantum mechanics. And quantum mechanics was developed around 1920s, 1930s onward. So people started getting a more theoretical understanding that what happens at the nanoscale. Before that, one did not. Before that, people wanted to apply Newtonian mechanics to understand this. But second thing is that, how do I see nano? I cannot see an electron. Even now, we cannot see an electron. We can only see the peripheral effects of an electron. Okay. For example, how do I tell you? For example, even if you can see the sun, it is advisable that you do not see the sun because of direct ultraviolet rays. But then how do I know that sun has come up? We know the light, the radiation that is outside. Then we know it's a morning, sunrise has happened. Similarly, till now, no microscope in the universe have been able to see an electron directly. Then how do I know that people are talking about single electron devices, single electron transistor? How do they know? Because electrons have their profound effect that you can observe by different experiments. That you can observe. So that is, so those kind of scientific instrumentation machines have been discovered in 1960s, 1970s. Very high resolution microscopes, electron microscope we call them, all these things have. So during the last 30-40 years, aided with the development of the basic science of nano, that is quantum mechanics, plus the discovery of the microscopes, high resolution microscope, we now able to see these nanomaterials very clearly. We now able to see the nanomaterials very clearly. So we'll go to, now the thing is that one dimensional. I will not come to heterostructure now, but I would like to say one dimensional. How many dimensions we live in? 3. What are these dimensions? X, Y, Z we normally say. If I tell you that a material is one dimensional, what will you understand? It is along X axis or along Y axis or along Z axis. So let's say this pen. It's kind of one dimensional, no, we can say roughly. So what happens? So our research in our lab, we are more concerned. So why we are thinking about, so consider that you have a copper wire, normal wires, electrical wire, and the electrons flow through them. We make these wires, to put it simply, our research, we make these wires in the nanoscale. So for example, what is the typical diameter of a copper wire here? Typical diameter? Less than a millimeter. If you see normal wire, 240 volt, 5 ampere wire, even less than a millimeter. Millimeter is quite thick, less than a millimeter. 15 ampere current flowing about. So then what is the thickness of this? Before even going to the, going to the microscope images, I want to tell you, I want to put the things into perspective. So what is the thickness of the nanomaterial that we deal in our lab? You touch your hair. Do you know the thickness of your hair? In meter, 10 to the power minus 5 meter. Minus 5? No, not that. Yeah, probably about 10 to 25 micrometer. Yeah, something like that. 10 to 25 micrometer means fraction of a millimeter. The things that we deal in our lab is about 1/100th of the diameter of the human hair. So from micrometer I am going to around nanometer, straightforward, right? It will be around 10 nanometer to 100 nanometer, something like that. Mind it, our target is to confine the electrons at that level, okay? Okay, now, so I'll go to, heterostructure is basically two different material we combine together. I will come to that in a later. So, introduction, background, these are just a research slide, don't worry. Now, I'll explain this slide. You see, I told you one-dimensional nanomaterial I told you, but then another layer of the research that we do, another feature, we call this vertically oriented nanostructure. You understand vertical? Vertically oriented, which is vertical. So, to explain that, I have these buildings. You can identify this building? Twin Towers, where? Malaysia Twin Tower. This is in Singapore. This is not so well known, I have just taken from internet. This is an office cum residential complex in South Korea, Seoul. Okay, so what do you find in common in them? What do you find common in these three buildings? I heard something, all of you are correct. Multiple structures are connected together. Connected. That thing is common. Connection, connection, connection. So, I will show you that the kind of nanostructures that we make in the lab, we further make them somehow connected like this. Okay, not all, but I will show you one of the main examples. So, why these are connected, do you think? Just for beauty or just for something new? What is for people to move? That means to make things easier for people. Functionality, we call it functionality of the building. We call, in some sense, probably safety aspect, ease of movement. So, these are called the functionality. So, we make our materials more functional, means more number of useful activities they can do for us. Okay. So, before going into the next, I would like to tell you, then what happens? Let's say there is some problem here in this building. So, people either can come down or people can quickly go to the other building using this connection. Similarly here. So, I will tell you, we make some nanomaterials from, let's say, a support, and then we wrap them with another type of nanomaterial. The idea is electrons from one of those nanomaterial can quickly travel across that bridge to the other nanostructure. So that is we call as heterojunction, means two different materials are combined together. So now I told you about the heterojunction. So our research mostly focus on, one major part of our research focuses on this kind of structures. So on the application side, not to worry too much because the theme of this lecture is nanomaterial fabrication through chemistry. So I will not go to the application part that much, but we work on solar energy utilization. So one of the aspect that we work, we make the nanomaterials, then you are all familiar with solar cells, right? What solar cells do? They absorb sunlight and they create electricity. It is a little different concept here. The materials that we prepare in the laboratory, they absorb sunlight and they help in carrying out chemical reactions. Our target is not to draw electricity. Our target is to do what is called in chemistry called catalysis. Have you heard about the word catalysis? Catalysis is a process to make difficult chemical reactions easier. No, we call them catalyst. So the theme of our research is photocatalysis. Photocatalysis is that the catalysis that is run by photons means light. Which light? Sunlight. Okay, I cannot say that I am doing any good to the world if I make a material and then say, hey, I need thousands halogen bulb to do my research. No. Then what good I am doing? I am burning electricity to do, say, I am doing. So we do it. So one of the application is we split water. I will not visit that part, maybe a little advanced at your level, but just want to tell you, split water into hydrogen and oxygen with the idea that hydrogen you can use in fuel cells and everywhere. Now you see hydrogen driven bus, fuel cell driven bus, and this is. So the first thing, okay, here is the photocatalysis. I will not come into that much, but I will tell you this. Yeah. Yeah. So I will come to here. Okay. As you say that how do I, so one of the material that we make are TiO2. TiO2 is titanium, we call it titanium dioxide. Okay. TiO2 nanotube. Why TiO2? TiO2 is a material which is extremely stable. Okay. And then TiO2 is a good photocatalyst material. But our contribution has been to make TiO2 material in this small, can you see here on the top, what this is an electron microscopy images. You see a lot of open nanotubes from the top, as you are seeing from top, there is a bunch of nanotubes from top. So again, so this is probably not very clear, but this scale bar, this is an electron microscope image. The scale bar here is not very clear, but I am telling you, this is a 200 nanometer. So that means typically one of this tube, if you take the diameter of one of this tube, about 100 nanometer or so. That is about 100 to 1000 thinner than our hair. Now you get the idea that what we are seeing there. So you cannot see them using a normal laboratory microscope, which is optical microscope. You have to use electron microscope, and that's a different topic altogether. I'm not going to visit that topic, that why you need electron microscope, because with optical microscope you do not get this kind of resolution. So there is an electron microscope. So now I will just tell you in a more simpler way that how do we make these nanotubes. As the theme of this talk is nanomaterials through chemistry, so I will more focus on how do we make, and the experiment minded, the experiments are so simple that you can go back to your school lab, you can tell your chemistry professor, and he or she can arrange this for you. You can make it yourself, and truly believe me, you can make it yourself. So that is why. So what we do, it is called electrochemical anodization. Electrochemical anodization. So anodization. So, or simply an so what we do, we have a beaker. In the beaker we take some, what is called, we call it an electrolyte. Have you done a very basics of electrochemistry? Do you understand what electrochemistry means? Electrochemistry is simply that you are doing some chemistry under a kind of a battery type of setup, an electrolytic cell. So what we need an electrolytic cell? 2 electrodes. That is the most fundamental thing, like, right? 2 electrodes. So we have one electrode dipped here, the other electrode dipped here. This solution is slightly acidic solution. Acidic solution. I'll come to that. Why we need acidic solution? What do you mean by an acidic solution? Acid dissolved in water. Simply acid dissolved in water. You know what? All of you know what is an acid? You know. Any example? H2SO4, HNO3, HCl, and something like that. Okay. So acids are chemicals whose pH in a solution remains less than 7. Very good, less than 7. So we take an acidic solution and we take 2 metals. One of this metal foil, I think you are seeing, those who are working in my lab, you are seeing this. The others I can show you sometime now or otherwise. And the other, we want to make, mind it, we want to make titanium oxide nanotube. So one of the metals that we take, metal is titanium. Here titanium is little bit expensive, but then it allows you to do some beautiful simple nanochemistry. Okay, so one of these is titanium, and the other one what I take, usually again little expensive, platinum we take, but you don't have to be a platinum, it can be a graphite rod or something which can withstand acidic solution for a couple of hours. You mind it, our material, whatever we are dipping in the acid should be stable for a few hours at least. So here we take a platinum and here we take titanium. So this titanium metal, and we connect it to some battery, okay, and we call it anodization. You understand what is an anode? Which is connected to positive supply. So that's why I have drawn the titanium which we want to make nanomaterials for is connected to the positive part of the battery power supply. Okay, and you apply typically from something like 50 to 100 volt for about couple of hours, 2 hours, 3 hours, something like that. You don't have to do mind it anything else. You prepare an acidic solution, you dip one titanium and one platinum into that, about a few centimeter gap, that's all, simple beaker, normal laboratory beaker, 100 ml, 200 ml beaker, half of that electrolyte, and then 50 to 100 volt from a good stable DC power supply. DC power supply, not these plugs. These are AC. We are talking about DC power supply. Why DC power supply? We want constantly one type of polarity on the die. If you apply this power through an AC power supply, what will happen? Titanium will be positive, negative, positive, negative, positive, right? So we don't want that. So titanium is connected to the anode. That's why the process is called anodization. So what happens? When you take out this, you wash it off and you look under microscope, then you see these beautiful nanotubes have formed. Don't have to do anything. Just that you leave it 2 hours, you take your tiffin, you take your lunch, you have some WhatsApp chat or whatever you like to do. You don't have to really do anything. Only thing you have to be careful in a campus like IIT Madras that monkeys do not come and snatch everything. I'm joking. Okay, monkeys do not enter our lab. We are careful enough. Humans are monkeys. They behave like monkeys. That's a different thing. Okay. So then what? Now the thing is that I will tell you what is happening. This might be the next natural curiosity for you to understand what is happening. And second curiosity you must have now that, oh, so simple, I can make nanotube. Can I make it in any metal? The answer is no. Not every metal you can make nanotube like this. So first I will tell you that how these nanotubes are forming. These are called self-assembly. Self-assembly means this is what nature does. Now what is happening? Mind it. If I show you this thing, there are two things acting on titanium. What are these two things? One is the chemical process. Acid is acting on the metal, titanium. Second, an electric field is also applying. Where is the electric field? Because I have applied a potential. So that's why it is called electrochemical. Chemical process plus electric field, right? So what is happening? When you take titanium, this is titanium metal, let's say, so I will explain it in a more detail. You take titanium metal. This is a titanium metal, okay? I have just drawn a large thick image, so on a horizontal way. So when you dip it in the acid solution, what acid solution does? Acid solution has a tendency to etch. You understand what is etching means? It is a tendency to dissolve the things. That's why some things which cannot be, simple example, at home, our mom, sometimes things get, some sticky thing, and we put some vinegar, we put lemon and leave it for some time. What vinegar and lemon? They are acids. They are weak acid called organic acid. These are inorganic acid. Organic acids are weak. Weak means even if you touch with hand, don't unnecessarily touch, but see, lemon we touch, right? You don't harm, but these acids never. So this weak acid, what they do? They etch out the top that food particles or the oil and anything on the utensil. So that same thing happens here. If you dip it in the acid, so acid will try to make small holes here. Why holes? They are digging out. This is chemical process, natural. Acid has a tendency to dig out. Wherever there is some weak, some pores are normally there, they will dig out. So what will happen? Some small holes will be created. Holes. Okay. Mind it, simultaneously there is an electric field is applied. And what is the direction of the electric field here? Direction of the electric field is here, like this, right? Between two electrodes. So here the electric field, I am showing it in a horizontal manner. So the electric field. So what this electric field does? When the digging happens by acid, the electric field actually accelerate the digging process. Means it will, whatever loose atoms are created, metal atoms, since this side is positive, the other side platinum is negative, they are dug out very ferociously. You understand? Very accelerated. So the depth of these holes increases. You understand? Depth. Just like a person is digging a well or a pit, digging. Simply it is an electrochemical digging. So with time what happens? There are lot of these holes are dug, and resultant what you see is all these holes are very close to each other. Now there should be one question, that why this part is not dug? Why this part is not dug? Why the entire thing is not flat? Why that there are certain part where there is material, certain part is dug? That is how the natural electrochemical process works. This again will answer the question that not in all metals you can make nanotube like this. So what kind of metal? Group 4 metals. If you look at the periodic table, group 4 metals: titanium, aluminum, hafnium, vanadium, like that metal. These metals have the particular tendency that they can withstand the electrochemical etching process to allow you to make this tubular structure, these holes, digging of the hole. For example, if you put gold or platinum, they are extremely stable. Nothing happens. That's why I was talking about putting platinum as the counter electrode. Nothing happens to platinum. Platinum is such stable. Nothing happens. No acid can do anything. But there are other metals called more softer metals: iron, copper, not aluminum, iron, copper and like. If you put them, they cannot sustain acid like this. So what will happen? If you just leave one iron foil or copper foil in acid, you see, after some time it vanishes. Simply vanishes means what? It has dissolved. No, means the copper atoms are all come out of the foil and slowly the foil itself disappears. Means all copper atoms are dissolved in the acid. So only for particular metals like titanium, vanadium, hafnium, aluminum, we can get this kind of sign. But I will strongly urge you, when you go back to your next class and you talk to your chemistry teacher, it's a simple but very inspiring experiment of couple of hours only to see that you can grow nanomaterial on your chemistry bench. Only thing that you need an electron microscope to see that you have really created the nanomaterial, and that electron microscope I can provide you. If you come with your sample, I can provide you, I can make you see that yes, we have created. So this is something that I wanted to talk about. And so see, this is what we can create. We can create this. Here you see there is a little difference. There are gap between the nanotubes, as you can see. So how do you create? But here there is not much gap here. So these are all that you can adjust the conditions of your bath here. Bath means the beaker here. pH control, concentration control, temperature control, time control, all these things controlling here and there, little bit up and down, you can do lot of parameters and you can create this. See here, what do you see here? These are conical nanostructures. You can see roughly, probably you can see here. The bottom side is wider, the top side is narrower. Conical nanostructures. This is also one beauty of electrochemistry, that you can play with a lot of parameters and you can create different types of nanostructures. I will also show you that we have created what is called multi-leg nanotube, means I will shortly show. So one nanotube here, then there are like two stands like this, going like this. Okay. Now I will come to this. Okay. Yeah, I will come to this. Now here you can see these nanotubes and there are multiple. Now I did not go to the details of the that background here. Yeah, it is not there anyway. So here, this nanotube, you can see some very thin plastic like thing are wrapping onto this. Can you see this? So we call this graphene wrapped cobweb, just a funny name I had given, graphene wrapped TiO2 nanotube. Are you familiar with the word graphene? What is graphene? No? Carbon atom, a plane of carbon, a sheet of carbon atom. Ideally, only monolayer means only one carbon atom thick, okay, and there. So now you see, understand what that buildings and connections mean. Now you understand why I showed two buildings and one connection. Now you see these connections between two. So I will tell you why we were interested to do that. The thing is that we realized that if we make these nanotubes are fine, they are beautiful structures, but we want that lot of electrons to travel through that, okay, but at the same time we wanted some kind of interconnectivity between the nanotubes. When we talk about interconnectivity, the electrochemical process itself does not allow us to create some bridge like that what we were seeing in the buildings. So what we decided, we thought about designing a material that we have this titanium oxide wrapped with, just wrapping with graphene and the graphene. So how did we do graphene? That's a different thing. I will not go to that detail now. So when we wrap with graphene oxide like this, that means now what you see is that most of the nanotubes are connected with each other. Most of the nanotubes are connected either from the top here, as you can see here, most of the nanotubes are connected with it. So this improves the catalytic performance of the nanotube. I talked about catalytic catalysis, catalytic performance of the nanotubes under sunlight. So what is called, this graphene wrapping enhances the photocatalytic performance of the nanotube. So this is again something I think those who are working in our lab can see. What we do is that since you are here for a short duration, but whatever we can see, as I told you, that if you find them enough interesting, you can, and we don't get a chance to see these things or in our laboratory within your RSIC program duration. You are all from Chennai. You can come back anytime during the summer break or later on. You can contact us, you can come back. I'll be very happy to show you the things. Okay. And now I will go to, I'll not talk about this. I will go to one more thing. I'll just come here. Yeah. This is another interesting work. So, you have all seen cactus type thing, cactus, or forget cactus. A main stem of a tree and then branches. No? The branches have all the leaves and which actually. So here you see a nanostructure. Here you see again, these are electron microscope images. Here you see these nanostructures. So see, there is a main stem type thing here, which I am pointing with the red arrow, and we are calling it Cu2O. Cu2O is called cuprous oxide. And what is CuO called? Cupric oxide. So what we have created here, we have created a core, that is the stem, which is of cuprous oxide, and then again horizontal branches which are of cupric oxide. So I will just tell you first what we have created. We have created a heterostructure. Now I am coming to that word, heterostructure or heterojunction. Why I am calling it heterojunction? Means the junction between two different materials. Cuprous oxide and cupric oxide both are in general copper oxide, but for chemist or physicist or scientist they are different materials. Okay, so I have created a structure which is a combination of two different materials, but I have created with a purpose. I have created with a purpose. Again, I'll not go to that detail of heterojunction physics, but we have created with a purpose that I'll tell you. Now, before that, I'd like to tell you what did we do. So, what did we do here? Here the technique is not electrochemical anodization. Here the technique, what you can see is, it is called hydrothermal technique. What is hydrothermal? You have all seen pressure cookers in your home, mostly probably. Yeah, pressure cooker in the kitchen. What a pressure cooker does? Why it is important? Why cooking is done in a pressure cooker? Compared to an open vessel, what is the additional advantage you get in a pressure cooker? Yeah, so there is a pressure in addition to temperature, and that pressure actually helps in the boiling point. Okay, so absolutely almost in the similar way, we have small mini pressure cookers. Only thing that pressure cooker does not give out whistles or anything. We want the material to be under pressure for a certain duration, and we fill up with similar kind of acidic or other solution. So in this particular example, what did we do is that we put a simple copper foil. Copper foil means a copper sheet, pure copper sheet, inside a solution. In this case, that was an acidic solution. Mind it, here is KOH. KOH is potassium hydroxide, which is a basic solution, alkaline solution. We put it inside and we leave it under 200 degrees centigrade. So what happens? KOH solution means KOH mixed with water. 200 degree means it's all water vapor along with KOH. So like acid, alkaline medium also HS material. That is why we can clean our clothes or utensils with soap solution normally. What is soap solution? It's an alkaline basic solution. Soap is an alkaline material. No, it's not acidic. It's a basic thing. Okay, but that also has a property that, you know, at the pH of high pH, 13, 14, maximum is 14, right? At a pH of 13, 14, it etches. So what happens that the copper foil is etched and you get this kind of hairy structures, as you can see here, this needle type structures that emerges. Again, all these we cannot see by eye. You have to look it through the electron microscope, not the optical microscope. So, but then what happens that Cu2O means cuprous oxide. What is the difference between cuprous oxide and cupric oxide? I mean, this is a bit more technically involved thing in chemistry, but you can tell me. I mean, apparently you say one is Cu2O, one is CuO, but what more you understand from these two? Charge. Yeah. Lattice will be different. Yeah, that is there. Okay, I'm trying to understand, I'm saying. One is, if I say, one is here copper is uniformly oxidized. Here copper is less oxidized. Do you understand why? Because here one copper has one oxygen atom. Here two copper has one oxygen atom. Do you understand my statement? So this Cu2O has a less oxidation than CuO. Got the point? What I'm trying to make? One copper is associated with one oxygen. Here two copper has one oxygen to share. So that means what? It is simply the oxidation of copper. If I can control, means I can control the the parameters, chemical parameters inside my pressure cooker, that reaction, hydrothermal reaction vessel. I can achieve less oxidation little bit. I can achieve this Cu2, and then again we run. So it is like we have made one dish from the egg. We boiled the potato or something, we take it out, we mix with potato with something, again we put it back in the pressure cooker for another run of cook. So that is exactly we do. We take it out in the first stage, this thing, and then we put another. So now when you take out, you see these horizontal structures which are CuO that forms. Now here you should dispute me immediately. You should tell me, ask me, sir, you did the same thing. You first put it in a pressure cooker, you got this hairy structures. Second time you put it in pressure cooker, you are not getting hairy structures, you are getting still something on top of this. Why? This is a very good question. Now the point is that I will tell you, the conditions for the first and condition for the second are somewhat different. We have different temperature conditions, different pH, little different pH and concentration that we change. I am not going to that detail because that is a research level things. Unnecessary you might get confused. What I want to tell you on a more practical thing, that in the second stage, why these hairy structures or why these spikes appear from this stem? Because in the second stage also almost similar thing happening, but now the copper sheet is already covered with this hairy structure. There is no way the hairs can grow from the bottom. So what the hairs have? The hairs have already formed the stems, and then the branches, I mean the chemical now in the second stage are deposited on to this hairy structure that form, and they grow over time and form the branches. So this is again called nucleation and growth. And why we now get a better chemical, CuO? Because we now ensure that the oxidation is complete. And once the top part is oxidized, the inside part, the stem, still remains Cu2O, because the top part is already covered with CuO. The inside part cannot get oxidized anymore. You understand the trick? So the inside part remains oxygen deprived. Oxygen deprived means Cu2O, one oxygen less per Cu or per 2 Cu. You understand the point? So we get this Cu2O-CuO heterostructure. We call it Cu2. Again, this is also simple chemistry, but generally hydrothermal vessel may not be at your school level, that may not be there compared to this. This is a little college level experiment. If you can say that's a bit of college or university level experiment, but your chemistry prof must be knowing about that if you talk about that, and you can come. So I will see, this actually explains the, yeah. That process? Huh. Can it be made? Yeah. There are a lot of options. I did not talk in detail about this. You are saying that it is okay. This is a potentiostatic process. You are talking about galvanostatic, where I send a constant current. So what will happen? Yeah. So this is a good question. There are some metals while people report. Problem is that since the oxide layers are forming, there is a potential drop across the thing. So we do not worry about how much current is flowing. We want to keep the electric field constant. Current is not our focus here, but the electric field is our focus. So we make it potentiostatic. Very good question. We make the voltage constant, current gradually falls. We don't worry about current falling. So galvanostatic, there are certain conditions where people report galvanostatic. More or less, this is the accepted norm. Because we want the electric field to be same, which does the digging part. No, electric field is electrochemical. Very good question. So now the last part I will come to here. Okay. Yeah. So I'll just come to here. We have almost 5 minutes left. How much time, sir? 5 minutes, right? Okay. So now the third thing, again vertically aligned bismuth ferrite BiFeO3. Don't worry about this compound bismuth ferrite. But I want to tell you again a simple, very simple way to create nanomaterial. So what I want to create Fe2O3 nano rod. We are not talking about nanotube now. The last one was nanowire. First I talked about TiO2 nanotube. Then I talked about copper oxide nanowire, thin wire. Now we are talking about nanorod. Nanorod is simply that the ratio of the diameter to length is higher. So we call it thicker. Nanowire and nanorod are similar thing, thicker. So now, do you know what this is called in the common language, Fe2O3? Rust. Rust. Simply you go outside an iron piece lying for a few years, not even years, few months, you get a brownish, reddish, brownish thing on top. Rust. What is rust? It is Fe2O3. Is just for to complete the discussion, Is Fe2O3 is the only oxide of iron? Answer is no. There is another oxide called Fe3O4. Fe3O4. What is the difference? Similar difference of Cu and Cu2O. One is more oxidized, one is less oxidized. Which one is more oxidized? It is more oxidized. That's why it is very, very stable. You see 100 years, you can see rusted things. Rain cannot wash off rust. Fe2O3 is much, much, much stable than F. But there is a very spectacular scientific difference between them. Fe2O3 is non-magnetic. Fe3O4 is magnetic. Okay, but we are not talking about Fe3O4 now. But as a curiosity, it may come to you that, sir, why you are talking about, can we create Fe3O4 nanorod also? We can. One of the students is now working. So Fe2O3, we wanted to make beautiful nanorod of Fe2O3. Okay, rust. You may say, sir, why you are interested out of anything in rust? Why you are rust interested? So I'll just briefly tell you that Fe2O3 can absorb sunlight very efficiently. It has a band gap, what is called a band gap of 2.1 electron volt, which absorb the UV and visible part of the radiation. So if you talk about solar energy active material, then Fe2O3 is one of the very, very promising material. So we wanted to create this nano. So what we do? We take, this is called ferric chloride, FeCl3, ferric chloride, and we mix it with hydrochloric acid. And you know, here you do not need any electrochemical thing. Here you do not need any hydrothermal pressure cooker also. It is another beautiful chemistry, simple chemistry on display. What you need only a constant temperature of about 90 to 95 degrees. You can just keep it in an oven, open oven, 90 to 95 degrees. Even if you do not have an oven, you take a hot plate, a heater. Only thing you have to ensure it is, if it goes beyond 100 degrees, what will happen? What will happen? FeCl3 solution is made in water. So everything will boil off. Everything will boil off. I will not get anything. Right? So 100 degrees we don't want to reach. We want to reach only 90 to 95. You didn't sleep well last night, looks like. No? Okay. So now we just keep it like that. Okay. 95 degrees for about 2 to 3 hours. But what we keep, this is an important part. I said you vertically aligned nanorod or nanotube, that is our research focus. In the first stage TiO2 story, I have the titanium foil itself which acted like a support from which buildings are not done in space, buildings have the ground as support, right? Similarly, in the first case, I have the titanium foil as the support to create nanorod. In the second case, I have copper foil itself. In the third case, we call it a conductive glass. Conductive glass. So you are all familiar with the word glass. Glass. No, here, I mean somewhere glass. This is not glass now, but originally. So glass, there is a layer, thin film which is coated on top of that. I will not go to that part now, but which makes the top layer of the glass conductive. Mind it, when we say conductive glass, it is not that the entire glass is acting like a copper metal. No. Only a thin layer, only one side of the glass becomes conductive. We have to put that layer, that conductive glass, dipped into that solution, and when we take it out, we see this nice, beautiful nanorods around. Automatically, you don't have to do anything. Again, this experiment you can do in your school, high school chemistry lab without anything, you know. And then what you can do, but the point is that if you get something like an unstable compound which is called ferric oxyhydroxide, not exactly, there is a different name I am forgetting, FeOOH. This is a kind of an unstable intermediate compound. Now I want to make it a stable compound, Fe2O3. How do I make it? Nothing to worry. You just put it in a furnace at 450 degrees C, or the same oven where I make it, you take it to 450 degrees C, you keep it for 2 hours. What happens? OH dissociates and leaving, there is a chemical reaction with the additional oxygen in the air and leaving Fe2O3. So what you get is finally, okay, don't worry about this part. This was part of another, how I make bismuth ferrite, that is As of now, that is not part of this lecture, and I will show you. It is not very clear, not very clear, but as you can see, you will not see very clearly now, but these are just like that. If you put it under electron microscope, you see nice rods. What is the typical, these rods are bit squarish, and what is the side length of the rod? Around 50 to 100 nanometer. Similar, I said 100 through 1000 times of the here, similar thing. And this is one thing I will tell you, recently we have been doing that. Just with this I will conclude the talk here. We have made lot of these nano stuffs. Gradually we became interested to know how one single hair behave. Hair means those nano thing will be. How do I do that? This is quite a research level work that the students go to again an electron microscope and they scratch out these things, these tubes are from the support. So what you get single this nano wire, nano tube or nano rod. Okay, then they put it on another support which is already some electrodes are made. These are all pictures in the nanoscale. See, 1 micrometer is the length, scale length here, 1 micrometer. Then we put one single nano wire and we do entire thing under a microscope and we put electrical connections. We cannot see them openly. It is openly all I can see a silicon wafer. But when you see under microscope, all these are done. I am just briefly telling you, this is the exciting thing we are doing. Okay, and then we can measure how much current it can flow. See, as a scientist, one should be interested not only creating the material, I should also know its properties in and out. Then only I can tell the technologist or the engineer, look, I have created a material with these features or properties. Now you want to use it for something, these are the properties, these are your limitations or what is called the range where you can use it. So this we want to know, we did this to understand how much current one can flow. We have found quite a few microamperes of current and which can flow through. At what current that single nanowire breaks? Why it will break? I am asking you, this copper wire, these are designed for 5 ampere domestic supply. You want to put 100 ampere through this, what will happen? Burn means what? Physically, physics wise burning means what? V is equal to IR. V is equal to IR, Ohm's law. So, or what is called the power, that is the heat radiation is equal to I square R. So, everything has a finite resistance. When you put more I compared to what it can withstand, due to R, there is what is called the ohmic heat will produced. Heat, and that heat itself will so-called burn it, means melt it. Similar thing happens in everywhere. If you try to send electrons in a much higher density compared to what that can withstand, what will happen? It will produce its own internal heating effect. All those electrons will collide with each other. So what will happen? That collision will create heat. That heat will exceed the melting temperature of that whatever material. It has a melting temperature. It's a solid material. It will have a melting. When that melts down, we have seen that it breaks in between. You can see these things we have precisely pointed out. We have investigated and we have found out at what temperature, at what voltage, not temperature, at what voltage, at what current one single nanowatt or nanotube will break. So that we know if someone is going to make a device out of it, we know that what is the limit of this new thing that we have created. Okay, so all these things we are doing, and so this is another copper oxide single CuO nanowatts. These are not made by any chemical technique, but I just wanted to tell you these are much more hairy and very sharp needle type. These are created just by putting a copper foil in a oven or furnace, but at a higher temperature, 500 degree. So at 500 degree, what happened? The top layer of the copper oxidizes, naturally oxidizes, but then what happens? You all know what is stress? Stress. No, this is called stress. When something is tightened, this is So the stress of an oxide layer is different than of a metal layer. So the oxide layer feels more stress due to the thermal expansion of the metal. Metal is below, top is oxide. So this oxide layer try to just come out. And this is again some complex, mechanical and physical process happens where they come out just like this. And what you see finally is this. Of course, I am telling you so simply, lot of studies have been made to understand how do I control the length, how do I control. But this is again, we did that, as we say, again we did those kind of study where we wanted to measure in one copper oxide nanowire and all these things, different things. Okay. So I think I will stop here because some other studies, this is a long presentation. I mean, I didn't want to edit and all. I thought I'll just tell you a story of this, what we met. So with that, I think I can, this is the lab. I think some of you are already visiting this. We have another lab in the second floor, first floor. This is the group. We have the students. Some of them are not here. Some new faces are there. Last year we organized a conference here where that's my son just joined in. No? So so we all, our group, my email is this. Okay. You can write somnath@iitm.ac.in. You can write me anytime. Somnath@iitm. So I do reply to the emails. Mind it. I do reply personally. I do not have any secretary or anything. So if you have really any queries, you want to meet up sometime else. So with that, I already crossed, I think, by 5 minutes. Thanks to you all. It's very, very glad to meet you. And anytime you are welcome. That's all I can say. You are welcome. Thank you.
On behalf of all of the RSIC students, sir, I would like to really thank you for coming here from your busy schedule and giving us this lecture. As the topic suggested that it is truly an exciting world of nanomaterials, and the different processes for synthesis of the nanotubes, wires and rods were really interesting. Thank you so much for this experience, and we are really eager to visit your lab, sir. Thank
Anytime.
you.
Thank you so much.
I would also like to thank the RSIC management and PSBB management and IIT Madras for this opportunity.